To analyze a rigid body that remains at rest in static equilibrium, we'll need to know our options for choosing rotation points, and we'll also need to understand the conditions under which the object will tip and begin to rotate. So here, in this example, we have a massive beam supported by these two posts here at points A and B. So our free body diagram shows a contact force from post A and a contact force from post B, and then the weight of the beam effectively acting right here at the center of mass of the beam. So our beam is uniform, center of mass right in the middle, but our posts are not equally spaced around that center of mass. So these will in general be two different supporting contact forces here. First lesson is that any point can be a point of rotation. We can imagine, we're free to imagine the beam rotating around any point we like. So point A, for instance, could be our rotation point, in which case we can imagine the beam sort of tipping around point A like that. Or we can imagine B being the rotation point and the beam tipping around point B. We can even imagine that point C over here, which isn't attached to anything, we can imagine that being the rotation point, as if the beam were going to drop down and fall through the floor that way. Realistically, we know this isn't going to happen, but for the purposes of computing the torques and establishing our conditions for equilibrium, we're free to pick any point to be our point of rotation. So let's see how that works. I'm going to have three columns here. This column is for the torques that are exerted if A is our point of rotation. This column for the torques that are exerted if B is the point of rotation, and over here if C is the point of rotation. Throughout this, we'll remember our right-hand rule. If we let the k-hat direction, the z direction, be out of the page, then a torque that points out of the page, get your right hand, thumb pointing out of the page, and out of the page torque would tend to cause a counterclockwise rotation. So counterclockwise by default is our plus k-hat direction. Flip that, and in the minus k-hat direction, thumb into the page, that would be associated with a clockwise rotation. Okay, so these are our defaults. If A is our point of rotation, then this contact force at A exerts no torque. It's acting right at the point of rotation. If B is our point of rotation, then this contact force FA would exert a clockwise torque around B. We would take RAB crossed with FA, R cross F, thumb points into the board, clockwise rotation. Post A pushing up this way would tend to rotate the beam clockwise around point B. Likewise, if C is our point of rotation, we also get a clockwise torque from force A with respect to point C. But the torque about C would be different from the torque about B, given these two different distances here. And of course, as we've already noted, there would be no torque about A from FA. In this next row, I've got the torques exerted about points A, B, and C, all from the weight of the beam. M naught is the mass of our beam, so M naught G, the weight of our beam. We see that that weight would be exerting a clockwise torque around point A counterclockwise torque around point B, and a counterclockwise torque around point C. So this would be a torque in the negative Z direction, in the plus Z direction, and in the plus Z direction. So part of what we're seeing here is how the same force can be exerting torques that differ not just in magnitude, but also torques that differ in sign, depending on your choice of point of rotation. Then here, I've got the torque exerted by force B if we choose A, B, and C to be our points of rotation. So we're getting a positive torque from force B with respect to point A. Of course, no torque about point B. And then a negative torque with respect to point C from force B. All right. Let's now compute the net torque with respect to point A. So that would be these three diagrams here. Point A is our point of rotation. I've got three forces. Each of those forces could be exerting a torque about point A. Let's find that net torque. So that'll be R cross F for each of these three forces. So there is no R here. That force is acting right at A, so no torque about point A from that force. Then R naught A cross M naught G there, and then RBA cross FB, those two terms. I've shown in orange here that the angle between our two vectors is a right angle in both of those cases. So we can compute the torque by doing the magnitude of the distance times the magnitude of the force times the sine of the angle between them. That's 90 degrees. And then we use our right-hand rule to determine whether our torque is in the minus k hat or plus k hat direction. Okay, so simplifying this, we would write that the net torque about point A in the z direction, so the z component of our net torque is given by this sum here. One negative torque clockwise and one positive torque counterclockwise. All right, so there's our net torque with respect to point A, but we're free to choose any point to be our rotation point. So we could also compute the net torque with respect to point B. So that would be the torque found from these three, the torques found from these three diagrams here. One clockwise torque, one counterclockwise torque, and then zero torque about B from that force right there. So sum those three terms. And that would look like this here, these three cross products. This one's going to go to 0. And then we just have magnitude of distance times magnitude of force. It's sine of 90 in both cases, since those vectors are at right angles to each other. And then our right-hand rule gives us negative k hat and plus k hat. So that simplifies down to this. So compare these two lines, the net torque about point A and the net torque about point B. They both involve one clockwise and one counterclockwise term. One clockwise, one counterclockwise term. I would like you now to pause the video and work out the net torque with respect to point C. Imagine that point C is our rotation point, so the beam is swinging around this fixed point here. Sum those three torques, simplify the expressions, to get a simplified expression comparable to this one or this one for point C. Pause the video, take a moment to write out those terms following the model I've shown for A and B above. Are you ready? You got it? Okay. We will have three torques here. None of them disappear since none of those forces are acting at point C. So three different torques. This one will be in the negative z direction. This one also in the negative z direction. This one in the positive z direction. So if we simplify those three expressions to get the z component of the net torque about point C, we'll have these three terms here. Okay. So that's computing the net torque about some point. Now, we're imagining that the beam is not rotating about any of those points. We're imagining the beam to be in static equilibrium, which means that the net torque should be 0. And now a theorem for you. Theorem is this. If the net external force on a body is 0, meaning the system is in what we call translational equilibrium, the center of mass is not accelerating. If that's true, then our theorem is asserting that the net torque on that body will be the same about every point of rotation. This is what I mean when I say that we are free to choose any point of rotation we like, A, B, C, or any other point. We're free to choose that point because it doesn't matter. The net torque will be the same about any point. So in particular, if a system is in translational equilibrium, the net force on it is 0, so its center of mass is not accelerating, and also in rotational equilibrium, so that the net external torque on the system is 0, then, according to this, if the net torque is 0 about some point, it'll be 0 about every point. The net torque will be 0 about every single point. So if we're trying to guarantee that the system is in static equilibrium, then we can sum the torques about any point of our choosing and set that equal to 0 and get a valid equation. Where did this theorem come from, you ask? Well, I didn't prove it. I'm just saying it's true. But you want to know? You sure you want to know? You want to see? You want to see a proof? You want me to show you that this is indeed true? Are you unconvinced? All right, here we go. Here we are. Here's a proof of the theorem. Suppose there are n forces acting on a system. The torque about point A due to the ith force is given by this expression. The net torque on the system about point A is given by this expression. Consider then another point of rotation, B. So A is our first point of rotation. Now we're imagining some other point of rotation, B. These vectors are related as such. And such that the torque about point B due to the ith force is this expression. Then we can write this, which separates into these two terms. And this would be the net torque about point B. So here we have the net torque about point A equals the net torque about point B plus this term. We're using the distributive property of the cross product. And we see that if the net force on the system is 0, that's this, the net external force, then if that term vanishes, proof that the net torque on A is equal to the net torque on B for any points A and B. A and B were arbitrary points. This indicates that the net torque on the system is the same for any choice of rotation point. Aren't you glad you asked? There we go. Prove that theorem. Now let's see how we can use it to set up some useful equations.